All right, so thanks for the introduction. And so I'll be talking about our work on DISTAL, the Distributed Tensor Algebra Compiler. So tensor computations are ubiquitous today in modern computing applications, ranging from simple things like matrix vector multiplies, matrix-matrix multiplications and additions, onto much larger and more complicated expressions, such as those that contract multiple operands or operate on higher order data. And these tensor computations arise in applications like scientific computing, such as quantum chemistry and physics, the tensor factorizations that arise in data analytics, and of course the various computations that arise in machine learning, particularly neural networks. And at the same time, modern machines are becoming more distributed in parallel, ranging from the multiple GPUs attached to a workstation, clusters of GPUs, and large government supercomputers. So in order for users to target ever-increasing dataset sizes and tackle new computationally difficult problems, we need to be able to effectively target these machines. However, programming these machines directly is pretty difficult. Users need to partition their data across the different memories in the system and write distributed algorithms that communicate data between the disjoint memories. So ideally, we'd like to have distributed tensor algebra libraries that end users can write their code at a high level and not worry about the details of programming these systems. So if we look at what a distributed tensor algebra library must support, well, in order to support the variety of use cases I kind of mentioned before, we need to be able to support all of tensor algebra. So we need to support things that have not just binary operands, and we need to be able to support higher order tensors, not just matrices and vectors. Next, we need to be flexible in the way that we talk about how data is distributed across the machine. Tensor computations are going to consume data from the rest of the application and output that data back to be consumed by the application itself. And thus, the system needs to be flexible in the way that you can describe how data is coming in and going to leave. Finally, the system should actually achieve peak performance. These kernels are going to be key kernels and key computations in modern workloads, and thus we need to be able to utilize all the flops and bandwidths available in our machine. So if you look at the state of the art, there's sort of going to be this trade-off between how performant we can be and how much of tensor algebra we can support. One particular end of the spectrum is an approach known as the library of kernels approach, and one such example of a system here is the scale-pack library, which as it sounds, the library is going to package together a bunch of different kernels for specific computations, and these computations are going to be specific to a data layout and an algorithm and the actual computation you want to run. However, you're going to achieve the peak performance possible as these kernels have been hand-optimized by engineers over many years. At the other end of the spectrum is a technique known as factorization, which is something used by the Cyclops tensor framework. And the key idea here is you can take any tensor computation and sort of reduce it into a series of matrix multiplications and transposition operations. And Cyclops is going to take this to the distributed setting by kind of just using a distributed matrix multiply rather than a one that runs on your single machine. However, so while you can express all of tensor algebra with this approach, you're going to lose out on performance. In particular, our experiments show that you can lose a factor 2 to 4x here, and even an order of magnitude in certain cases. So a way around this is to utilize compilation, and our particular compiler DISTAL is going to allow you to attack the generality of tensor algebra by actually having a compiler and then generate specific code that is tuned to a particular computation to get both performance and generality. Additionally, through the compilation, we're actually going to be able to express different ways of being flexible about how your data is distributed, which neither of these systems can really do for higher order data. So in order to write a tensor kernel, let alone compile it, you have to specify three things. First, you need to specify what you actually want to compute, the actual computation you want to do. You need to then specify how your data is distributed across the machine. And finally, the algorithm that you're going to use to compute on it in a distributed manner. So our compiler DISTAL is going to take these three inputs and output you code that runs at a scale from a workstation all the way up to a supercomputer. Okay, so I've given you the high level of DISTAL now, and I'm going to talk about the specific three input languages you're going to use to describe these things to the compiler. So first, to describe what to compute, as you may have seen in Peter's talk before, we're going to adopt the notation that commonly is used to describe tensor programs called tensor index notation, and it basically implements the Einstein summation notation for describing tensor codes. So here we have index variables that sort of correspond to nested loops, and variables that appear only on the right-hand side are going to correspond to these sum reductions. So this is an example of a matrix multiplication written out in this notation. Next, to talk about how data is distributed, we introduce a little sublanguage called tensor distribution notation. And I've given an example of the syntax at the bottom here, but I'm not going to talk about it in this talk. Please see our paper for more details about the actual syntax. But the key idea of this language is to basically describe for each dimension of a tensor, is that dimension partitioned across the machine or replicated across the machine? And with just that specification, we can express a wide variety of things such as row and column major layouts, tiled layouts, and even more for talking about higher order data. Finally, to talk about how computation is distributed, we're going to utilize a scheduling language. It's common to many prior works. And so we're going to include various commands that, we're going to include a number of commands for like single node execution, like loop, splitting, fusion, reordering, to optimize code on a single machine. We're going to introduce some new commands that talk about distributed algorithms. So the first such command is distribute, as it sounds. You're going to be able to describe that the iterations of a particular loop should execute across all nodes in your system or all GPUs on your system. Next, we introduce a command called communicate. And so this command is a purely optimization-only command. It does not affect correctness of your program. And it allows you to specify algorithmically when should communication occur within your loop nest. So you don't have to specify kind of what indices of a tensor need to move around. You just say algorithmically, I want to communicate this tensor around in blocks at this particular level of my loop nest. And finally, we introduce a command called rotate, and it's going to act as a distributed symmetry breaking operation to enable the expression of systolic communication patterns. So with these three different input languages, our first big result of our paper is that we can show that this language is extremely expressive. In particular, we can express 50 years of history of matrix multiplication algorithms, dating back to the first matrix multiplication algorithm, Cannon's algorithm in 1969, recent advances in communication avoiding algorithms in 2011, and the most recent algorithm, Cosmo, in 2019. As these algorithms all have very different communication patterns, some have a systolic pattern, some organize the processors in a three-dimensional grid and perform reductions across these. But if you look at that through the lens of DISTAL, where you specify how the data is distributed, and then how the computation is distributed through a scheduling language, you can express all of these different computations. And I want to stress that these are real DISTAL programs. You can take these and run them. This is not like this is not a sugared up version of the code. So I've showed you that the language is expressive, and at the same time, DISTAL is going to allow you to compete with hand-tuned programs just using these primitives. So here I have weak scaling experiments on the Lassen supercomputer running up from 1 node to 256 nodes. And so this is on a distributed matrix multiply, a kernel that has seen significant effort from researchers to optimize in the past. So on the left is CPUs, the right is GPUs, and basically higher is better here. We're reporting the number of flops achieved per node as we scale out. So we compare against the Cosmo library, Cyclops Tensor Framework, and Scalapack, all of which package high-performance matrix multiplies. And DISTAL is going to achieve pretty competitive performance with these systems, achieving 95% the performance of Cosmo on CPUs and 85% of the performance of Cosmo on GPUs. And this is with nothing matrix multiplication specific about it. So at the same time, being able to compete with hand-tuned code, DISTAL is going to generalize that high performance to the full range of tensor algebra. So here I have weak scaling results again for various higher order tensor computations written out here, and we compare against the Cyclops Tensor Framework library, which, as I mentioned, is going to use this factorization approach of reducing everything to a series of distributed matrix multiplies. And so the specialization DISTAL gives us allows us to do things like write an algorithm like this top right here, we can write an algorithm that doesn't communicate at all versus CTF's approach that will. Or for the bottom kernel, the MTTKRP kernel below, we can implement an algorithm that has been published and bounds have been proved on rather than sort of a generic algorithm before. And so this approach is going to give us between 1.8 to 3.7x speedups and even a 45x speedup in an outlier. All right. And because we utilize a compiler, we can compile to GPUs and get even larger speed up here. So here we don't know of any distributed multi-GPU libraries that let you, any other libraries that let you execute tensor computations across clusters of GPUs. So we compare against just our own CPU implementation. And here we can see that for bandwidth-bound applications, we can get 3 to 4x speed up. And for compute-bound applications, we can get an order of magnitude by being able to utilize GPUs. So I've talked a bunch about the kind of theoretical and practical benefits of DISTAL. So now I want to take a bit of a deeper dive and talk about how you may actually use DISTAL to write some programs. And so to do this, I'm going to talk about deriving the summa matrix multiplication algorithm in DISTAL. And so the summa matrix multiplication algorithm is used in Scalapack for its distributed matrix multiply, and it's known as an outer product matrix multiplication algorithm, meaning that if you take your matrix multiplication, we're going to outer order the K loop outside. So we're going to take sort of column vectors of B, row vectors of C, and we're going to take an outer product between these two things to get temporary like tile of the output, and then we'll accumulate that into the output to actually perform the computation. So the summa algorithm is going to distribute this in the following manner. First, it's going to take all the processors in your machine, and it's going to organize them into a two-dimensional grid and tile the input matrices A, B, and C onto those processors, as I've written out here with the as I sort of drawn out here. Next, rather than considering one vector of B and C at a time, we're going to look at just chunks of vectors from B and chunks of vectors from C at a time. And so we're going to do outer products between these chunks of vectors. So now the way the communication is going to happen here is the processor, so in our processor grid, the processors that own the current chunk of vectors from B are going to broadcast that chunk of vectors across their row in the processor grid. And the processors that currently own the chunks of row vectors of C are going to broadcast those down their column in the processor grid. And kind of the intuition for why this works is consider we're trying to accumulate this output tile in A that I've shaded blue here. So right, the chunk of that vector it needs to outer product is going to be the piece of B within its current row in the processor grid, and it's going to need the current set of rows from its column in the processor grid from C. All right, so that's kind of the basic idea of how the SUMA algorithm works. So now let's recreate this in DISTAL. So the first thing we need to specify is what we want to compute. So we already looked at how to specify this in tensor excitation before. So we can write out a matrix multiply. Now we need to talk about how the data is distributed. And intuitively here, we need to partition both dimensions of the tensor. Kind of if we partition the rows and columns of our matrix, we're going to get a tile distribution across our machine. So I've written out the syntax for doing this in our sublanguage here, but you can look at the paper for more details. So finally, let's actually schedule the computation now, assuming we've placed the data where we want. And so the way I'm going to represent this, I've got the sort of code down here, and I'm going to apply transformations to it on the right to change the loop structure. And I'm going to try and have a visual representation of that computation at the top. So we start here with a standard matrix multiplication loop nest, where we're sort of doing the inner products algorithm. And the first thing I'm going to do is I'm going to tile the I and j loops such that I've got a loop for each tile, and then within each tile, I perform a local matrix multiplication. All right. The next thing I'm going to do is I'm going to split the k loop such that it operates in chunks and reorder it such that we do an outer product algorithm now within each tile. So here I've got a loop for each tile, for each chunk of vectors in B and C, do a matrix multiply. So here we've got kind of the same loop structure as SUMA. We need to now distribute it and set up the communication to make everything work. So I'm going to first utilize this new command distribute, which I'm going to say I want the loops over all my tiles to be distributed. So each machine is going to now construct each tile of A in the output in parallel. So now I need to just schedule the communication to make everything work out. So first, I'm going to communicate A underneath the loop for each tiles. So you can imagine here, as the pseudocode is saying, when the program starts up, every processor is going to go allocate and get that piece of A that they need to accumulate into. And then I'm going to say I want to communicate B and C underneath the loop for each chunk of K. So as the pseudocode now says, every processor is going to, whenever they start their loop of the current chunk of B and C, they're going to go request that piece of data that they need. And thus, because sort of every processor is, every processor is iterating over K in the same way, they're going to all request, like everybody in the current row of B is like going to need that same piece of B, and same for the same column in C. And so this is going to, this code actually re-implements the SUMA algorithm as before, sort of from a, sort of in this loop transformation-based framework rather than low-level MPI code. And I'll stress again that this is valid DISTAL code. And if you write it, you're going to get a code that performs competitively with Scale-a-Pack. All right? So I want to conclude now and leave you with a couple of thoughts. So first, DISTAL allows you to achieve both high performance and generality in distributed tensor computations. And the key idea here is to allow for separate specifications of how your computation and your data are distributed. And with this separate specification, you can implement a wide variety of different algorithms from the literature for your arbitrary computations. And so in the future and ongoing in future work, so first we've looked at taking these ideas and adding sparsity to them. Kind of, can you take the same abstractions I provided here, and just by changing the format of your tensor to say now it's a CSR matrix, can you get a distributed computation on that sparse matrix? And next, of course, as Peter talked, we want to remove this burden of scheduling from the users. If a user doesn't have to think about schedules, suddenly now we can let users who don't know anything about distributed programming take advantage of a supercomputer for their computations. So that's going to conclude my talk, and I'm happy to take any questions now.
So your Milan Kulkarni, Purdue University. Your conclusion slide actually, the thing I was getting ready to ask you until your conclusion slide came up is, okay, so how do you do sparse? And But I wonder even whether the same abstractions are always going to work. If I think about how people often do sparse in parallel and distributed settings, it often winds up looking more like things like graph partitioning and distribution of graphs and things like that. So I was wondering if you could comment on that.
Yeah, so luckily, so this paper, we just got the good news that this is actually going to be published soon, but the kind of idea here is, so you actually can keep the same abstractions. You can say that, for example, for an SPMV, if you're going to multiply, multiply your sparse matrix and a vector. So you can say if this format of this matrix is sparse, like it's CSR, sort of the first dimension is stored densely, second dimension is stored sparsely. And the compiler sort of has enough information to say, oh, if I want to do a row-based distribution here, I can distribute the I variable of this computation, to get an algorithm that iterates, that sort of distributes the rows of this matrix. And we show extensions to this data distribution language to allow you to talk about different ways of distributing that sparse data across your machine in the first place. So you can keep a lot of these abstractions the same to talk about sparse data.
Very cool.
So if you have NUMA architectures or multi-GPU architectures, this can be expanded to deal with that?
Yep. So this, that was one of the things we want to start out with doing. So this distribute command can sort of be applied hierarchically. Same with the data distribution. So in this, let me see if I can just go back. So in this code here, as algorithm here that we actually use, a lot of these. So to tell you a little bit of the Lassen supercomputer, so each node has 4 GPUs and it's two sockets per node. So what we often do is for the particular algorithm here, we implement an algorithm at the node level. So the nodes will communicate with some granularity, and then within actual node, we distribute again to then write an algorithm that either distributes across both sockets of the machine or just communicates locally within the 4 GPUs on that node. So it's sort of built to take advantage of the hierarchy in these machines.
So in this slide, I see that in some instances, Cosma has done better than DISTAL. Did you look into the reasons as to why Cosma is doing better? Is it because there's some gaps to fill in the scheduling language?
Okay, so the slight difference here on the CPUs is because, particularly we target a dynamic runtime system called Legion, and so Legion is going to take some of the runtime resource, some of the CPU cores away to perform dynamic analysis. So there's going to be a slight performance drop here because it's going to utilize like 2 threads on the machine from that analysis on the CPU, so that's what causes the small deficit here. In particular, in the paper, we have an experiment that if you drop those 2 cores per node from Cosmos, well, it's going to have nearly identical performance on CPUs. On GPUs, I think there's a couple. I don't want to go into too much, but kind of there's a little bit of a different implementation here of Cosmos sort of going to do all this communication in CPU to CPU. While on this particular machine, we appear to have problems if you try to directly copy from a GPU to another GPU across the network, there was some performance degradation there. So I think it is mostly some implementation details that I think that could be pushed into the runtime system to fix. Yeah. But again, Cosma is also a very specialized library for exactly matrix multiplication, and we don't have that specialization at all.
Hi. Yeah. Thanks for the talk. So I was wondering, is there ways to describe something that will not work? And so my question goes into, I have these 3 specifications. Is there some interaction between what the specifications are doing? And is there a way, because I didn't hear anything about like respecting semantics, respecting dependencies and these kind of things. So do you deal with that? I imagine, but how?
So right as of now, so so the key idea, you don't have to, there's going to be a separation between how you describe your data and how you schedule your computation. And so there's no correctness problem of making those things match up. It's purely a performance problem. Sort of course, if you have your data distributed in a column manner, but you want to iterate it over in a row-wise thing, you're going to have to do some sort of global transpose to like get that to work out. But that's not a correctness problem. It's only performance. But I mean, it is possible to supply an invalid schedule, but the compiler will tell you that that's a problem and not compile it for you.
Okay, I think that's all we had time for.